So welcome to Introduction to Numerical Optimization. In the beginning, this session will be recorded, so if you later on have any questions, you can raise your hand and you will get a microphone, and then everyone in the room can understand you, and also the people who watch the recording can understand you. As you've already seen in the last few minutes, we have here some installation instructions. I hope many of you have already completed them. Can we get a quick raise of hands maybe? Who has cloned the repository and created the environment? Okay, not so many yet. Maybe you can try to get this done until the first practice session, or also at the beginning of the first practice session there's a lot of time for the setup. And if you have any problems, then just raise your hand during the practice session and someone will come to you and try to help you. The GitHub repository also contains a PDF version of these slides. So if you can't read this on the Beamer, you can maybe check out the PDF version. The mic is on. It's a green light. Yeah. Okay, I can also try to speak a bit louder. Okay. Yeah. If you have any trouble understanding, raise your hand and we'll try to find a solution. So quickly about us.
If you understand, if you hear everything, raise your hand.
Okay, that looks good. Yeah. So my name is János. I started the SDMagic package, which you will see in this tutorial or later on, in 2019. I'm currently a postdoctoral researcher at the University of Bonn. My background is actually economics, and I'm currently looking for interesting jobs. So if you know anything, let me know. And
yeah, my name is Tim. I'm as a core contributor to SDMagic. I'm doing a PhD in economics at the moment, focusing on computational econometrics. And yeah.
And then maybe we can also get some feedback on you. So first about Python skills. So who has at least 1 year of Python experience? Raise your hand. That's almost everyone. Who has done some kind of numerical optimization before? Almost everyone. Who has used scipy.optimize? Who has a favorite optimization algorithm? So, yeah, have a few hardcore optimization people here, but no problem. Maybe at the end you will have one, or you will actually learn that you need multiple favorite optimization algorithms. So we have 4 sections to this tutorial. We start at the very basics, introducing what actually is the goal about numerical optimization. Then we introduce you to scipy.optimize, which probably most people have used before if they did some optimization in Python. It's the go-to package with quite a few algorithms. And then we introduce SDMagic. That's the package we have been working on. And that's actually not a package that implements its own algorithms, but it wraps algorithms from many other packages and provides a nice interface to them. And you will see quite a few nice features of SDMagic during this tutorial. We then talk about 2 important problems. One is choosing an optimization algorithm, which is the most difficult aspect of numerical optimization. Often makes a huge difference whether you choose the right one or wrong one, can make a difference of orders of magnitude in runtime. And then we talk a little bit about global optimization. In the very end, I give you some resources. If you want to go deeper, then you can look at them at home. The structure of each topic will be that we first give you a summary or a preview of the exercise that you're going to solve, so you already know what you have to look out for. Then we introduce some theory, or let's say the mechanics of using a library in very simple examples on the slides. And then you immediately afterwards solve a slightly more difficult version of this example. And then Tim is going to take over and discuss the solution to this example with you. So after this discussion of the solution, everyone is on the same page, and then we can continue with the next topic. So first, we do an introduction to scipy.optimize, and the practice session is going to consist of two things. First, you get the math equations of one objective function that we want to minimize. You translate this math notation into Python code, and then you use scipy.optimize to minimize the function, and later check whether you got to the right solution. The example I'm going to show you on the slide is very simple. So what is numerical optimization all about? First of all, we need a function we want to optimize, and that's typically called the objective function or criterion function or just f or sometimes fitness or energy surface or whatever, depending on the literature you're reading in. We are mostly going to call it a criterion function in this tutorial. And here we have a very, very simple criterion function, which is just a function of two parameters, a and b. And the criterion value is actually the sum of the squares of the parameters. So this has all kinds of nice properties. It's convex, it's additively separable, and very easy to optimize, but a good way to show you the mechanics of how to use scipy.optimize. The parameters of we want to optimize over are a and b in this case. Typically, they will be collected in some kind of NumPy array. And what we want to get is the argmin or the objective value of at the argmin, a star and b star. And then possible extensions to such a problem could be that we have constraints or bounds that the parameters need to fulfill. That makes it a bit harder, but we are really just looking at the very simple problem here. And as you can also see in the plot on the right side, the global optimum, and it's also the only local optimum, is at a star equals 0 and b star also equals 0, and the function value is also 0 at this optimum. How would we do that with scipy.optimize? First, we import NumPy, and we import the minimize function of scipy.optimize. We then code up our function that we had in math notation on the previous slide as a simple Python function. Here for scipy.optimize, it's important that we cannot have like the two arguments a and b. Instead, we need to collect those two numbers in a one-dimensional NumPy array. And then in the first row here, we unpack these two numbers into variables and do our calculations and return a scalar number in the end. Then, since we're using local optimizers, we need to set up some kind of start parameters. We're just choosing a vector of 1s of the length 2, because we have two parameters. And then we can call the minimize function from scipy. The first argument is our criterion function that we coded up. The second one are the start values, and then there could be more, for example, a method argument for choosing a different optimization algorithm. And then we can look at the result after minimization. It's 0.0 as function value, and also the optimal parameter is 0. So this worked. What is scipy.optimize? It's a unified interface to 14 different local optimizers. Some of these optimizers support bounds or constraints. You will later see what we mean by bounds and constraints if you haven't seen it before. And they all have the same interface, and so they all expect the parameters to be in a one-dimensional NumPy array. And for example, if you want to do a maximization, you need to flip the sign of your objective function and then minimize the objective function with that flipped sign. And if you have some other needs, so if you, for example, need a global optimizer or you have a special structure to your problem, then you can use a different interface that's also in scipy.optimize that we're not going to cover here today, because we will later see some other ways to do that. And after this very short introduction, we already go to the first practice session, and Tim is going to take over.
Thanks. Yeah, had to activate the microphone. Okay, so you find all the materials here on our GitHub page. If you clone that and open the directory, you will see that it looks kind of like this. So you have an exercise folder, you also have a solutions folder, and you have the environment. Has everyone activated or created the environment yet? Okay, so most of you, that's good. Now you will have a little bit more time to do this in this first exercise session round. So let's open this up. Now, in the first optimization, as Janos just said, you're going to use scipy.optimize to optimize the function. You will find a little bit of resources here and a description of what to do below, and then your tasks. Now, if you have any questions regarding the exercises, just raise your hands. And after the 12 minutes, we will come to you, or we will present the solutions. And if you have questions, we will come to you, or you can come to us. But that's it. You have 12 minutes. Okay, so the 12 minutes are up. Again, quick raise of hands. Who has finished all of the tasks? Okay, at least some hands. Let's discuss the solutions. Okay, so for task 1, you were asked to implement the Criterion function so that you can use it with scipy.optimize. And one feature of scipy.optimize is that the input vector is a flat numpy array. So the first thing you have to do in your Criterion function is you have to pass the vector x into the variables ABC. And of course, there are also other ways that you could implement this, but this is how we approached it. So we defined the first entry of x to be A. Now B is a vector. So x from 1 to 4 is B. And then C is a matrix, so everything else in X is that. And of course, later on, when you define the start parameter, x naught, you have to keep this in mind. We'll see this in task 2. And then the definition of the value is just implementing the math. Okay, so that's the solution for the first task. For the second task, you were supposed to set up the start parameters. And for simplicity, we assumed that all the starting values should be 0. Now, here we just write x naught is equal to a vector of zeros, 8 zeros, but where does the 8 come from? And so we have to count parameters. When we go back to the math, we see that A is a scalar, so we have one parameter. B is a vector, 3-dimensional vector, so we have another 3. And C is a matrix, a 2x2 matrix, so we have another 4. So in total, we have 8 variables in this optimization problem, so we need a flat array of length 8. Okay. For task 3, we were actually supposed to use scipy minimize. Now, this is just a call to the minimize function from scipy. We can call it, we pass the function f and the starting value x naught, and we get our result. Now we can look at the result, the resulting parameter under res.x. And yeah, this now doesn't tell us a lot. So we have our assertion code provided. For this, again, we have to pass the result into A, B, C, and then we can call our assert functions, and we realize we actually got the solution up to 6 decimals. Do you have any questions? Okay. If this is not the case, we will continue with the lecture. Oh. Number of, yeah. So you could consider, so I would have to run all of this notebook, but there are some additional informations in this result object from scipy.optimize.
I think it's result.nfev for function evaluations.
Thank you.
Okay, then we continue. So let's first discuss the pros and cons of scipy.optimize. So pros. Okay, can you hear me now? Yeah. So let's first discuss the pros and cons of scipy.optimize. One obvious pro is that it's a very mature and reliable library, and actually all the algorithms in there are battle tested and quite bug-free. You don't need any additional dependencies because in almost any project you're using scipy anyways. You have a relatively low overhead because most of these optimizers are implemented in C or Fortran. And you have enough algorithms for many use cases. There are a few cons. So you have relatively few algorithms. If you have practical problems, you quickly run into situations where you wish for a few more algorithms. You don't have any parallelization out of the box. If you need to do a maximization, you need to flip the sign. And also after you got your result, you need to flip it back, which I often forgot. And then some more practical things that you get if you have long-running problems is that you get feedback only at the end, and if your code crashes, then you don't get any feedback. And also the parameters are a flat array, which even in our simple example in the exercise was already a bit limiting. So even though all the algorithms in SciPy are great, you often wish for a bit more convenience in practice. And let me show a few examples of where that would be the case. So one thing I struggled a lot with during my master thesis, for example, is that you hit exceptions. So the optimizers are trying out different parameter values, and they're very good at finding ones that somehow trigger numerical instabilities in your code. So if there's any ability that some matrix decomposition fails, typically your optimizer will find a value where this is the case. And then you would wish that you have at least some way of debugging where this happened. Also, in any larger project, you write typically a lot of boilerplate code. So this is an example from a real project from a colleague of mine. There are maybe better ways to do it, but there are also definitely worse ways to do it that I've seen in practice. But what he did in his project was really he gets this big parameter array, one-dimensional. Then he first infers some model properties, and then takes this parameter vector apart into a dictionary of smaller NumPy arrays that he then needs in the calculations. And in this particular project, when you made a slight modification to the model in question, then you often had, let's say you got one more parameter here, and then you had to adjust also all the other ones. So this was quite error prone. And also in practice, if you do this a lot, you will obviously make mistakes. This is an example where I feel very sorry for the authors, because the central result of the paper was actually invalid because they made this one tiny mistake. Out of 29 parameters, they took one out twice, and one they didn't use. So then it's basically an equality constraint between two parameters. And this, unfortunately, in that case, drove the central result of that paper. Also, switching packages is painful. So sometimes you tried all the algorithms and it didn't work. So you want to try some others. Some colleague says, yeah, but try out this package. Then you want to try it out. And it's not just that you have a different, let's say, syntax for instead of a minimize function, you also need a very different objective function because otherwise it won't run. And this is basically why some years ago we started SDMagic. So I first give you again a preview of the practice session. In the next notebook, you will translate the example you just had in your first notebook. If you didn't finish that, you can take one from the solution. We shared the solution also with you. You will translate that into using SDMagic minimize instead of SciPy minimize. So this should be quite easy because it works almost the same. And then you start actually using the features of SDMagic. So you will not put your parameters into a flat array, but something else. And finally, you will plot the history of the criterion function during the optimization. So what is SDMagic? SDMagic is a package that wraps optimizer from other packages. So we implement a few algorithms ourselves, but most of the algorithms we have are just wrapped from other packages. And we also don't modify the source code there. But we give those algorithms a unified interface, so no matter from which package the algorithm came, it will have a SciPy-like minimize interface. And some additional features that you will see in just a minute. On top, and hence the name, we also have some tools for nonlinear estimation. So if you estimate likelihood models or method of moment models, which we did a lot as economists, then you will find some tools to get standard errors for your estimates there. But if not, you can simply use SDMagic as an optimizer library. If you want, and that's what you're going to do in the next exercise at the beginning, you can basically just use it like SciPy. So you use the same kind of criterion function, don't need to make any changes. Instead of SciPy minimize, you use SDMagic minimize, and then our keyword arguments have slightly different names. One central difference is that there is no default algorithm, so we force you to think about the algorithm you want to choose, and this is because this default algorithm often gives a wrong sense of security of like, I did not decide anything, I just did what they told me, and optimization problems are so different that there is no one algorithm that can solve all of them. So here we want to force you to think about it a bit more explicitly. Then a big difference of SDMagic is that the params, so the start parameters, can be almost anything. In SciPy, they had to be one-dimensional NumPy arrays. That works here as well. But they could, for example, also be pandas objects. So they could be a data frame or a panda series. And one thing that already gives you is that you have labels for your parameters, so you can name them and don't need to remember that position 27 was that parameter. You can also do scalars, lists, or dictionaries. And if you want, you can also do name tuples. The most important thing is, and you already see that in the example of dictionaries and name tuples, you can nest all of these as deep as you want. So if you want to have a list of dictionaries of NumPy arrays, that's okay. You can do that, and SDMagic will run just fine. You might not want to go too deep in the nesting, but it's really nice that you can have either a dictionary of NumPy arrays or sometimes one more level of depth, so you can structure your parameters and don't need to do any of this complicated chopping one vector apart. Let's look at one example where we use this. So here our parameters are a dictionary that contains 2 scalars, and then the third entry is a panda series that has 3 entries. This is useful if you somehow need 5 named parameters and maybe want to use this as a vector but with labels attached. And then you simply write your criterion function expecting this kind of structure for the parameters, and you save in our example from the notebook, the first 3 lines of taking stuff apart. You can simply use them from this dictionary as you need. Then the minimization is basically the same again. Use criterion function, start parameters, and select an algorithm. And if you have a dictionary as start parameters, of course, the optimal parameters will also be returned in that same structure. We already had this question about how do you see how many iterations you had. So we have a slightly more verbose message by default. It tells you like where the function started, where it got, how many iterations it took, and so on. This depends also a bit on the optimizer. And then different optimizers have very different convergence criteria that are not always comparable. And one tentative attempt at fixing this is that we give you some more information on like how much has the function value and how much have the parameters changed in the last few iterations. And if you see many stars here, you can be quite sure that even if you made your convergence criteria a bit stricter, it would probably not change the results. You can also access all the elements of this optimization results, criterion value, number of evaluations, number of iterations, and so on. And we also have a history of all the parameters that were tried out and all the corresponding function values, so you can look at them. We also have logging and dashboard. So to activate the logging, you basically just need to pass a file to a database that does not have to exist, so it just needs to end in DB to the optimization. And then SDMagic will create an SQLite database and continuously update it each time it tried out a new parameter vector. This parameter vector and the corresponding function value will be saved in an SQLite database. And that way, it's almost guaranteed that you don't get any data loss. So even if someone shuts down your servers, you shut down your laptop, you don't lose any of your progress in the optimization. You can simply come back afterwards and look at where it stopped and continue from there. Another nice feature is that you can read this database already while the optimization is running. So if you're interested in whether your criterion value actually goes down and how fast and how much, then you can either use a dashboard, which you don't show in detail here, but it's in the documentation. So you get an interactive plot in a bouquet dashboard that shows your criterion value, or you can use this optimized log reader, where you can always look at the last few iterations or the full history, and you can do your own plotting if you want to do that. Another thing you can do is you make this criterion plot from it. So the criterion plot shows the criterion value over time, so over the different function evaluations. And this first argument here can either be an optimization result or the path to a log database. And you can already do that while the optimization is running, so you see what's going on. And maybe if you don't have any progress or less than you expected, you abort the optimization and do something else. You can also compare multiple optimizations here. So this could be also a dictionary of optimization results or a dictionary of path, and then you get more. Sometimes you get very extreme function values in the beginning, not in this case, but sometimes it jumps like to 10 million in the first iteration and then goes down again. So in that case, you might want to look at a monotone history that just shows you the current best value at each iteration, and you take out these extreme values. And if it runs very long but nothing happens in the end, you might also want to limit the number of evaluations that are shown in the plot. This is the example that I just talked about, where you compare multiple optimizations. So here we take 3 different algorithms, a Nelder-Mead algorithm from SciPy, the same algorithm from nlopt, and the fetus algorithm. We run all of them in a loop and stick the result into a dictionary. Then we pass this dictionary to the criterion plot function, and it plots all of this. And it's really nice, like if you take a second to appreciate that these are different libraries, like the optimizers. The optimizers are not even from the same library. You cannot just run seamlessly the optimizations with the same interface, but you can even plot all the results against each other, and all this history collection is implemented in a harmonized way. Some other features that we don't look into at in detail, you can calculate parallel numerical derivatives. So in case you don't have a closed form derivative, we can do that for you and in parallel on as many cores as you have parameters. There's also maximize. There's a simple syntax for bounds and constraints. Constraints are not supported by all optimizers, but many. It's compatible with automatic differentiation in JAX. So that's typically the way how I get derivatives in my projects. There is sensible error handling. So if you hit that linalg error after 5 hours, it would not actually stop. But if you want, it somehow tries to guide the optimizer back into a feasible region. And we have quite a few algorithms for nonlinear least squares problem, which I talk about in more detail later. This is a link to the documentation that you can check out during the exercise. In the exercise notebook, we also link to more specific sections of the optimization of the documentation, so you can look at them while you're working on the project. With that, I hand over to Tim.
Okay, so let's look at the second exercise notebook. So you will again have 12 minutes for this, and it's actually quite straightforward. You're just supposed to translate basically the results of the last exercise now to SDMagic. So use SDMagic instead of scipy.optimize. Yeah, that's it.
I try to use a plot, but my notebook window is empty. The plot is. Do I have to use a widget backend, or how do I do the plotting? The plot doesn't show up. It's just a big empty space. Right.
The plot is implemented in Plotly. We can have a look in a second.
Ah, yeah.
You have multiple renderers in Plotly. Maybe you can play around with that.
Thank you. I'm trying import SDMagic, even though I set up an environment and it makes an error for me for the notebook.
I'll come.
I don't know why. That's not the question. Sorry.
So maybe quick raise of hands who has finished the exercises, because I think we should slowly continue. Otherwise, we will run out of time in the end.
Okay, we will now discuss the solution to the second exercise notebook. So for the task 1, you're supposed to just provide a simple switch. So basically copy the Criterion function from the first notebook without any changes, and then use minimize from SDMagic. So we will first copy the Criterion function, and we have our starting value x0 as a NumPy array. This is just as in the exercise notebook 1. Now, here we call SDMagic or em.minimize. And as János already mentioned, the keyword arguments are slightly different. Now we have, instead of fun, we have Criterion. Instead of x0, we have params. And one thing that's also different is we do not have a default algorithm. So the question asks us to just use scipy and nlopt. If we run this, we can access the resulting parameters under res.params and the Criterion value under res.criterion. This is all you needed to do for task 1. Now for task 2, we should now look at more flexible parameters. So what we do is we define a starting parameter dictionary, start params, where we basically store the variables as we have them in mind in the mathematical notation. So we have a dictionary with entries A, and start value is 0, B, that's a vector, a 3-dimensional vector, so we have np.zeros 3, and then C is a matrix, so we have, again, a 2-dimensional 2x2 matrix with zeros. Now, the new Criterion function takes this, so it's now called X, but we will put in the start params, so a dictionary, so we can access the variables under these dictionary keys. So the code we had over here is basically redundant now. If we define it like this, we can still pass this to SDMagic using the new f and the start parameters that are a dictionary, and we get the same results, although the output shape of the rest.params are now the shape as the input or the start parameters. We can also call the testing code to see that all of the assertions are true. So this is what you had to do for task 2 with the more flexible parameters. Now for task 3, we are supposed to plot some algorithms against each other. That's of course very useful if you want to check if one algorithm performs better than another one. Here we will also use the nlopt nldameet. Remember that in the task 1 or task 1 and 2 we used scipy nldameet. We will now use the nlopt nldameet additionally. So what we do is we create a dictionary called results. Then we loop over these algorithm keys, scipy nldameet and nlopt nldameet, and just store the resulting optimization object in this dictionary under the algorithm name. Now, the results dictionary now contains the optimization results under these keys, and we can just pass them to the SDMagic Criterion plot function, and it will display these plots and the optimization results, so you can compare them against each other. And this is actually a nice example where you can see that although both of these libraries implement the nldameet algorithm, one, like the implementation matters a lot because the nlopt implementation just converges much quicker. So things like this are just really hard to see if you don't use visualization tools. And with SDMagic or these Criterion plots and other diagnostic plots you can find in the documentation, neat facts like this can be made visible. But that's it for the second tutorial. Any questions? Yes?
You use scipy directly or you use estimagic? Sorry.
Thanks.
If you use scipy directly and you use the same algorithm from scipy but from SDMagic, is there a significant difference in performance, like for the same number of iterations? Did you check that?
So you mean that if there's an overhead of using SDMagic? There's a slight overhead, yes. But we do actually have a fast track implemented in our code so that if you use NumPy arrays, then the overhead is for reasonable problems doesn't really matter.
So it would only matter if your criterion function is in the area of microseconds for one evaluation, then you will notice something. If it's, let's say, a millisecond, then you would already not notice the difference. If you use a very, very nested parameter structure, it might be a bit slower than that, but it's, typically there's not really a lot of overhead.
Okay, thanks.
I have a question on number of steps here. If you look at a graph, then you have a lot of steps where it looks like for the nlopt that you are very close to the target there. So how many steps do you do? How close do you get? Maybe can you zoom in the picture? Is this possible? No, because it seems like 90% of the steps are done very close to the result. So you do a lot of steps, maybe not necessary.
I mean, this is a monotone criterion plot. So the non-monotone would probably wiggle a bit more. So this only shows the current best value, only means there has not been an improvement. And the nldameet algorithm has kind of an exploration phase where it like tries out stuff in the neighborhood and then it makes a step goes to the best one. So this is, each time you have this exploration phase that you see as a flat line and then it makes goes a bit lower.
Okay.
Have you performed any comparative analysis or comparative study with respect to other optimizers like either scipy or some Bayesian optimizers like hyperopt or optuna based on for the runtime?
For some problem types, we have made quite comprehensive benchmark. And that's typically also how we select algorithms that we want to wrap. So we try them out, and if they perform really good in some kind of benchmark, we take them on. We have not looked at hyperopt or other of these hyperparameter tuning libraries yet, but that's on the list. So we want to add a lot more Bayesian optimizers, and then you could also compare them against these, but we have not done that yet. Okay, if there are no more questions, then we continue. One more question. Did you solve your... Okay, yeah. Next topic is choosing algorithms, and that's by far the most difficult topic of numerical optimization, and we are only scratching the very surface of this. We want to make this very practice-oriented. So we basically give you a few optimizers that we use a lot in practice and tell you when to use them, so you can choose and try it out. We don't go a lot into the theory. And in the practice session that corresponds to this section, you will actually this time already get code that does an optimization, because you already know how to do that. So we have a different criterion function, and we already give you all the minimized code. And this optimization will actually fail silently. So the optimizer will say it converged, but not to the right values. And then your task is going to be to choose an algorithm that works. And please don't just try them out one by one, but look a bit on the slides and try to also explain why you choose the one that you choose. So first, a very rough overview of properties that might be relevant to choose an algorithm. One of the most important ones is smoothness of the function. So is your function differentiable? Has it maybe countably many kinks? Has it discontinuities, or is it even stochastic? And depending on that, you need to choose different algorithms. Another important topic is convexity. Basically, if your function is globally convex, it means that any local minimum will also be a global minimum. And there are also some other nice things that can be exploited from this. So if you have a convex problem, it gets much easier to solve. Then you need to think a bit about the goal that you actually have. So, I mean, in math, we only write min and that's it. But you have to be a bit more pragmatic if you want to implement this in code. So you need to know whether you want a global solution or a local solution is good enough. And also what kind of precision do you have? Like typically you get out 5-6 digits of precision from a local optimizer, or 5-6 significant digits. If you want much more than that, you need to take some extra steps. Another important question is how many parameters do you have? So if you have 2 parameters, you can think about brute forcing a global optimization. If you have 100, this would be completely impossible. If you have something like 1,000 or 10,000, you can still think about using a second order method that needs to store a Hessian matrix. But if you have much more than that, you also need different optimizers. Then the question of bounds and constraints. If you have many constraints, typically only very few optimizers can handle them. So you already are a bit restricted there. And a topic that's often overlooked, and we'll look at this in a bit of detail later, is that you might have some kind of special structure in your problem. For example, many data fitting problems have a nonlinear least square structure. And if you have that and exploit it, you will get a much faster and much more accurate solution typically. And some of these theoretical considerations are very important, and then typically you should not end up with one algorithm that you want to try out, but with multiple, maybe 2, 3, 4. You try them out and you look at the plots that we already did in the last exercise to compare them and then see which ones work best. So SDMagic has quite many optimizers. We have all the optimizers from SciPy, the local ones, the global ones, and the least square ones. Another large library that we wrap is pygmo, that has many genetic algorithms for global optimization, and nlopt, which has also actually similar but more algorithms than scipy, and often the same algorithm has different implementations, like they have the same name, but one of them is better. So for example, the BFGS, especially the LBFGSB algorithm from scipy, is typically better than the BFGS algorithm from nlopt in my experience, but the nelder-meet in nlopt is much better than the scipy one. And then we also have some algorithms that are rather unknown. Sometimes there are packages that just implement one lonely algorithm, but if they're really good and were really useful in some project, then we also add them. I already mentioned like smoothness and differentiability as an important factor, so I want to give you some intuition on how derivatives are used during optimization. And for those who already know about optimization, this is probably doesn't go deep enough, but I just want to give you a rough intuition. So the first observation is that the negative gradient of the criterion function with respect to the parameters is a descent direction, or actually the direction of steepest descent. So then most optimizers use something gradient-like to find a search direction. Now, it does not have to be a gradient, it can be a finite difference approximation to a gradient, or it can even be estimated completely differently. But you always have something that is basically a slope, because we want to identify some direction where the function goes downhill. Then another observation is if you imagine a linear function, so just a straight line, and you have a descent direction, then you want to actually go as far as possible, because it only gets better in that direction. But if you have upwards curvature, you actually don't want to go so far, because then your descent direction is only valid very locally to where you were. And this hopefully gives you some intuition of why most optimizers use something Hessian-like to determine the step length. So use a first derivative to determine direction, and then a second derivative to determine how far they want to go. And for a very curved function, they don't want to go that far typically. And now I'm going to talk about, I think, 8 different algorithms that I use a lot in practice, and each time give you a very, very rough intuition of how they work and when to use them. So the first one is from scipy, the LBFGSB algorithm. It's actually implemented in Fortran. How it works, so this is a function that, an optimizer that needs a gradient. So either you pass in a hand-coded gradient, or one you get from automatic differentiation, or SDMagic can calculate it using finite differences for you. And then it approximates a Hessian from multiple gradients. So over the time, it accumulates a history of gradients, and from those gradients, you can somehow estimate the curvature. When to use that? So it's basically my go-to optimizer for differentiable functions with or without box constraints. It scales up to a few thousand parameters and has a very low overhead since it's implemented in Fortran. And as I already said, it beats many other BFGS implementations from the other libraries. Another optimizer that can be used in a very similar situation, so typically if I use LBFGSB, I also use FIDES and compare them, is the FIDES algorithm. This is a so-called trust region method. So it basically takes the same gradient and Hessian approximation as the BFGS algorithm, but it uses it slightly differently. Instead of a closed form formula and followed by line search, it uses it builds a Taylor approximation of the objective function, and then it minimizes this approximation to the objective function, which is much cheaper to minimize than an actual expensive criterion function. And the solution of this so-called surrogate problem is then the next candidate at which the criterion function is evaluated. And yeah, as I said, you use this in the same situations or similar situations as LBFGSB. It is more customizable, so you have many optional arguments that you can use to tweak how the optimization goes. And it works very well in cases where the LBFGSP algorithm is too aggressive. For example, you saw the linalg error earlier on the slides. This was triggered by LBFGSP, and actually the same optimization would run if you use the feeders algorithm. And I would say it's a very underrated algorithm because it's implemented in a separate package that is not very well known and has a rather peculiar interface. But you can use it via SDMagic, and I had great success using it. Then we move on to gradient-free optimization. So gradient-free optimization is if you don't have a closed-form derivative. You can use these optimizers, and they will try to do something better than a finite difference approximation to gradients. So what these algorithms do in particular, they evaluate the criterion function somewhere in the neighborhood of your current parameter guess, and then they fit an interpolation model on these points and optimize this interpolation model instead of the actual criterion function to generate a candidate again. So in that sense, they work like the feeders algorithm. They are trust region methods, just they don't need derivatives. And Bobika is basically my go-to algorithm if I don't have closed-form derivatives. There are slight differences in implementation, so nlopt has less overhead, and one from the numerical algorithms group has some advanced options if you have a noisy objective function. Both of them require well-scaled optimization problems, so that means that you should not have one very influential parameter and one where almost nothing happens. If so, you need to somehow rescale your problem that it gets a bit more uniform. Another derivative-free algorithm is the nlopt algorithm that you have already used. As we discussed after looking at the criterion plot, this has some kind of exploration phase where it evaluates points close to your current parameter guess, and then it always drops the worst one and takes on a new one and so on. And you use this basically in the same situations as Bobika, but it works better for badly scaled problems. Then I want to talk about the nonlinear least squares structure. Let's first look at the definition. So you have a least squares problem if your criterion function can somehow be written as this shape. So you have some arbitrary nonlinear functions, a bunch of them, and then they get squared and summed up in the end. And this arises naturally in most data fitting problems or many other statistical applications. And the syntax for doing this in SDMagic, which you will also get in the next notebook, is that you, instead of a scalar, you return a dictionary. Once you return the actual value, so this is the big F of x, and once you return the so-called root contributions, these are all the individual FIs. So this is a vector. It can actually be, as parameters, some more complicated structure, but something that looks like a one-dimensional vector then. That way, SDMagic has access to these intermediate results, and this can be used by some optimizers to drastically speed up your optimization problem. And for this, we also have, again, gradient-based and gradient-free optimizers. The gradient-based ones come from SciPy. Actually skipping this because we are short on time. The gradient-free one, we also have multiple, one from the numerical algorithms group and one from the toolkit for advanced optimization. So you would, whenever you have a least square structure, you should exploit it and use one of these algorithms. And depending on whether you have derivatives or not, you choose. And finally, there's IP-opt. And the only thing I have to say about that, it's probably the best open source optimizer for heavy nonlinear constraints. There are many closed source optimizers that are as good or maybe better than IP-opt, But if you want to use an open source optimizer and have many nonlinear constraints, you would use IPOpt. And with that, we get to the last practice session.
Okay. So for the third and last exercise notebook, you're supposed, or as János already told you, you will face an optimization problem that will fail silently. You're supposed to figure out why it failed silently and how you can choose maybe a different optimizer that doesn't fail. That's it. You have roughly 10 minutes, I would say. If you have any questions, just ask.
Maybe one thing to add, so you don't waste time. You don't have to look at the implementation of this criterion function. Like, we gave this to you because it doesn't matter and it won't have many hints on what to do. So look at what we write about it, but not at the math.
Do you happen to have any optimizers for maximizing the function? Like I saw in the docs, there is algorithms for both minimizing and maximizing.
So you can use all of these optimizers to maximize the function. You simply, instead of em.minimize, you use em.maximize.
Do you happen to have any examples?
We have them in the documentation, so maybe I'll look for an example and put it online. This is more.
So who's finished already? So we will do one more minute. Okay, then let's start with discussing the solution of the last exercise notebook. So in the first problem, you were given a modified version of the pole singular function from the Morean-Wild benchmark set, which contains differentiable nonlinear least squares functions. However, the function is modified by us. Especially relevant is this first line, or this is our only modification, where we round the input array up to 4 digits. Now, as you've seen, when we run minimize using scipy LBF GSB, you realize that the criterion value improved from 215 to 215, so nothing changed. And if we look at the resulting parameters, they are also stuck at the starting parameters. So the first task is to understand why the algorithm here fails and why it got stuck at the start parameters, and then maybe we will even find a better algorithm for this problem. Now, there are many ways to go about this problem, but one way is, or one problem that we have is we can't really, or we don't really have an intuition for what the function does. So if you don't have an intuition for what a function does, it's always good to look at a visualization or a plot. Now, we've also seen this is a nonlinear least squares function. So we have a lot of, or actually we have 4 root contributions here. And the input value x is also 4-dimensional. So it's in many ways a high-dimensional function or multi-dimensional function. It's not easy to visualize. One thing you can do, however, is to use a slice plot. You find the slice plot in our documentation. Here's a link if you look at the solutions. Now what the slice plot does is it tries to visualize the function and it tries to visualize the contribution of individual parameters. So if you look at maybe the top left figure, this is the plot that you get when you plot the function or the criterion value, where you fix the first or the second, third, and fourth parameter at their starting values, but then you basically evaluate for the first parameter the criterion function on a grid. So this is what we define here. We consider the function value at the start values, and then we have to provide lower and upper bounds. And these are all NumPy arrays. So this is the lower bound for all parameter values -1, and an upper bound for all parameter values +1. If you look at the plot and the x-axis in particular, we know that the starting value was 3, -1, 0, 1. And then we have the bounds, it's always -1 and +1. And now this gives you some kind of understanding how the criterion function looks like if you vary the individual parameters. Now, if you look at the problem like this, it looks pretty smooth. However, the rounding we performed was at digit 4. So maybe when we set the bounds at -1 and +1, that's just a neighborhood that is too large. So let's maybe call this plot again, but in a tighter neighborhood. So here we subtract 1 or 0.001, and we add it. So we have a really tight neighborhood around the starting values. If we look at the function then, we realize it's actually a step function. This is what the rounding does in the first line. Now, if we have a step function, of course, it's going to be pretty hard for a gradient-based optimizer to find the optimum, because it will just see or think that the gradient, or it will realize the gradient is 0, and it will think it's terminated. So this is the problem in this problem. And now one thing that you can do, or as Janos discussed, we can use a different kind of optimizer. In this setting, we use a trust region gradient-free optimizer, which has a least square structure. Maybe, yeah. Here we use the NUG DFOLS. And if we plug this in as an algorithm and look at the resulting parameters, we see that it actually found the solution up to some reasonable degree of accuracy. And one important note of warning is if you see something like this, you might think that, yeah, okay, we can always use a gradient-free optimizer because they may be more robust for cases like this. However, if you know that your criterion function is differentiable for sure, then you should always prefer the differentiable optimizer. And we have a few slides more left, so I think we will just need 2 or 3 more minutes, but then we're done.
Okay, and there's no additional practice session. So one more thing that I want to say is this looks quite artificial with the rounding, but actually things like that happen in practice if you somewhere lose accuracy or in some statistical problems. So one more thing I want to discuss briefly are bounds. You already saw them in this plot that you just showed. So they are lower or upper bounds on each individual parameter. And they can be handled by most algorithms that we have, and also by most cyber algorithms. Typically, these bounds need to hold for the start parameters, and then they are also guaranteed to hold during the optimization. So this is very good if you want, for example, the one parameter with a variance or probability that needs to actually be positive to be defined, then this is and how you specify them depends on how the parameters look like. So basically, you always mirror the structure of the parameters, but there's one exception. So in the case of a simple numpy array, the bounds are also numpy arrays. If you have only lower bounds, you don't need to specify any upper bounds. And if you just don't have bounds for some parameters, you can use np.inf or minus np.inf to relax those the bounds for those parameters. A special case in SDMagic is if the parameters are a data frame that have a column value, lower bound and upper bound, so then you can actually specify the bounds altogether, and only the value column is considered the parameter, and the rest are the bounds. And finally, if you have a dictionary of parameters or some other nested structure, you can typically only specify the bounds for a subset of the structure. So for example, in this case, we have a larger dictionary that contains the entries x and intercept. We only want a bound on the intercept, so we only specify the intercept here, and then we try to match that somehow. And if it's ambiguous, you will get an error, and then you need to match it. And then the last topic I want to discuss is global optimization. So far we've only looked at local optimization. This means whenever you find a flat spot, basically you stop and you're happy. And global optimization means that you want the global optimum of the function. And only for globally convex problems, these are the same. Examples where you might need global optimization are these functions. So there's the alpine function that has a few different values, and the active function is just very regular with very many different optima. And you can imagine that if you do local optimization for these two functions, you don't get necessarily to the global optimum, you just get stuck in the first local optimum. So one question we sometimes get is, can you do brute force for this, like just do a grid search? And here's why this doesn't work. So if you imagine that for each dimension you want a grid of 100 points, and then you get the cube of the square of that, the cube of that, and so on. And if you only have like 6 parameters for the simple case where the Criterion function takes 1 millisecond, you will also already have to wait several years before you get a result. So you need to be somehow better, smarter than grid search, but typically then you also don't really get a guarantee that you found a global. There are a few different types of genetic global algorithms. The first one are genetic algorithms. So they typically come from the pygmo package. So these are heuristics inspired by natural processes or natural selection. And they typically start by having a random initial population of parameters. And in each evolution step, they evaluate the fitness function or the criterion function on the whole population of members. And then they replace the worst members by some kind of combination between the better ones. And there are different strategies for that, and the different genetic optimizers use different strategies, and sometimes you can influence that. And here you also typically converge when you reach some computational budget, and not when you hit the flat spot or so, because that wouldn't tell you very much about this, whether you found it or not. Another type of optimizer is Bayesian optimization, which we don't have very much yet in SDMagic. So there you evaluate a criterion function on a grid or a sample of parameters, and you build a global surrogate model of the criterion function, and then in each iteration you refine that model, and at some point it should, and you try to refine it especially in promising areas, and at some point you have a very good image of your criterion function. And finally, another option would be multi-star optimization, which so you can use any estimagic optimizer in a multi-star framework. It works simply by setting multi-star equals to yeah, I think I don't need to summarize very much. So you solved a simple problem using scipy.optimize, and then saw some more strategies of solving optimization problems using SDMagic. I want to give a quick shout out to the team behind SDMagic. These are the amazing contributors. And if you also want to contribute, you can check out the last slides. So just make sure you get someone in contact with, communicate via Sulip. And also, if you like SDMagic, you can leave a star on it. Thank you very much.